Hello. The title of this presentation is Supporting Light Field Simulator Validation using ChArUco board for camera localization. There are total three technical terms here. One is, as highlighted, Light Field Simulator, then ChArUco board, and third is camera localization. Just to make sure that we are all on the same page about what these three terms are, I will take some time of this presentation to give some background about these technical terms, starting with light field simulator. So this light field simulator in our VAC lab is a computer program or a software that is mostly written in C++. It was developed by the VAC lab way before I started my honors thesis, and just like any C++ programming language, it has some source code. The source code is provided by the VAC lab. This source code is then made to some solution file. The solution file is then used to build the binary exe files, and these binary files are all we going to use to uh, run the simulator. Just like any computer program, the simulator also takes some input, gives some output, and the what input it will take or what output it will give depends on what is the work of this simulator. The work of this simulator is to simulate a field of light display. Now, what is a field of light display? I think it will be more helpful to know it visually. That so this is a video recorded in the VAC lab using a mobile camera. As you can see that when you look at this display from different angles, you see a different 2D scenes, and it looks like you are looking into some 3D holographic. And well, that's the reason that this field of light display is also known as a holographic display. When you look at it from some extreme angle, the you see that the part that is far from you gets blacked out, and you see only the part that is closer to you. uh, there is some angle within which you have to look at it, and that's when you get some 3D perspective. That is, you get the perspective as if you are looking out through some window into some 3D scene. Now, how can we validate a 3D display? The methodology, if we oversimplify it, it will be simply that we take a photo of the display that is showing some content, and then we give the same content to the simulator, and then generate some photo from that simulator, and then compare between those two photos. Right? Now, if we look at the first step of the methodology, that is display a light field in the light field display, this should not take more than a day, right? If we are not able to display a light field in the light field display, probably so we are using the light field display manufactured by a company called Looking Glass. We are using their 16-inch light field display. If we are not being able to display a light field in their light field display, probably contact the manufacturer that, hey, we are not being able to display anything on your light field display. What are we supposed to do? So this we can consider it done. This is not something that can be considered an honors thesis. Next step, display the same light field in the simulator. Now, as I said that I didn't make the simulator. The simulator was made by VacLab way before I started my honors thesis, and that simulator came with the instructions of how to run the simulator, and displaying a light field in the simulator was part of how to run the simulator. So we can consider this done too. Now coming to the third step, that get a photo of the light field from the light field display using a camera. Now, is that going to be a challenge, or will you not be able to get a photo of the light field display using a camera? I hope not. That's probably not the challenge, because we have a camera. We just need to take a photo of that. Now, that was the third step, and that seems to be fine. Yet, what then is the problem that it is an honors thesis? It's such a big project. Well, the problem is that we oversimplified the methodology. Let's dig a bit deeper, but I promise that I will still keep it simple. So to dig a bit deeper, we have to break the third step into some sub steps. That is, we get a photo, yes, but then tell the simulator every detail about the camera. And this involves camera localization, which was one of the technical terms we saw in the title. Now, what's camera localization? Camera localization simply means getting the position and orientation of a camera. It is probably not even that big of a technical term. There's not much of a concept. Just find the position and rotation of this camera. How can we find the position and rotation of this camera? But more important thing to ask is that what is this thing attached to the light field display? And by the way, this is the same light field display that you saw in the video uh, during the beginning of the slide. It's just that the light has been turned on while taking this picture. So what is this thing attached to this light field display? Is it some product QR code? Well, no, it didn't come with the light field display. It turns out that just last year there was another honor student whose name was Sadiq Bal. He, under the supervision of Professor Matthew Hamilton, did this camera localization. So I was not the first person to do this camera localization in Backlab. He did this camera localization but using an ChArUco marker. Here comes a technical word, ChArUco marker. What's an ChArUco marker? ChArUco, first of all, it's an abbreviation which stands for Augmented Reality University of Cordoba. The University of Cordoba came from the fact that this ChArUco marker was based on a research paper that was written by some researchers in the University of Cordoba in Spain. So this ChArUco marker is a fiducial marker that is often used for pose estimation or camera localization. So, by the way, pose estimation and camera localization, I may use these words interchangeably during this project. So, sorry in advance if that causes any confusion. So, uh, as I said, Sadiq Iqbal used ChArUco marker, and ChArUco marker is just one of the fiducial marker. It is not even the first fiducial marker ever that ever got invented. There were other fiducial markers before then. You can see this list of fiducial markers, and one advantage of ChArUco marker is that you can generate as many ChArUco markers as you want, because other markers, like before the invention of ChArUco markers, the markers that existed had some predefined set of dictionaries. Because they were already predefined, because they were not generated, what happened is that, let's say in some experiment you have some methodology where you need a large set of where you need a large set of fiducial markers. That's when you will have to think about, okay, do I have enough fiducial markers for my experiment? But the good thing is that for our project, for our methodology, because after the invention of ChArUco markers, we no more have to think about, do we have enough IDs for ChArUco markers or not. We can generate as many ChArUco markers of any ID as we want. We can use custom dictionaries. There is a whole paper about why ChArUco marker is better than other fiducial markers. So I'll just leave it to them. But just focus on the fact that ChArUco marker allows you to use as many markers as you want. And this is where also comes the thing that we can use uh, as many ChArUco markers as we want. We can use a board of ChArUco markers, like a board filled with ChArUco markers. And this board of ChArUco markers probably can be combined to some chessboard to make something called ChArUco board. So this ChArUco, which is another technical term of our title, came from chessboard plus ChArUco marker, and this is also implemented by OpenCV already. So now what we are supposed to do in our methodology, that is we use this ChArUco board to do 3 steps in our methodology. Our first step is to test our own methodology, that is our pose estimation or camera localization working properly. So to test our camera localization, the first thing we can do, it does not matter that what scene we are displaying on the display. If we want to test just the pose estimation part, just to test the pose estimation part, we can just use a solid color on the display, and then take like 3 photos of the display, and then um, tell the simulator where this display is, and then check between the simulators. So you can see that there are three different there are three different angles from which the photo of the display has been taken. In one photo, the display looks very close to the left edge of the image. Another photo, it looks very close to the right edge of the image. Another photo, I just cherry picked a location where where the content of the display looks like it is displaying something greenish, even though the content is a solid white color, just to make some interesting results. In our second methodology, what we did is that we displayed some simple 2D graphics into that scene with some basic geometric shapes and colors, and we did the same thing, that just take three arbitrary angles of camera, where in one it looks like the display is in the middle, another where the display looks close to the left edge, another where it looks close to the right edge. And then in our third methodology, we displayed an actual 3D scene, which is going to be our last stage of the methodology. That is, we again display a 3D, we display the same chessboard scene that we saw in the beginning in the video, and then we took like 2 photos where it looks close to the left edge and the right edge. And now it's time for the results. So, as I say, the methodology one is just to see whether our pose estimation is good enough. Let's see. We thresholded the colored pixels such as so that the pixels that are not black becomes white, and those that are black are just black. And then we do the absolute difference, and it looks more or less fully black image, the absolute difference of the two images. Then from methodology 2, we overlapped the two images such that it makes one image. This actually shows that there is no like when the simulator is simulating the display, there is no weird pixel mapping happening, because if some weird pixel mapping happened, some very, let's say the pixel mapping of the display in the simulator was such that some shape got very stretched, then the overlapping would not happen nicely. Let's say it would happen that the circle, the green circle you see, that would probably appear so stretched that it would look like some oval, and probably then the overlapped photo would look like some Venn diagram, like the two Venn diagram. Yeah, so that's not happening. It looks like it's the same image from the top, which actually reinforces that our uh, pose estimation is good, and also our simulator is not doing anything much weird. So it's a test of both things, and now it's time to test the final thing, that is, we want to test whether the 3D scenes are properly simulated, right? And this is where we have to manually check, because um, it is very hard using a computer to actually compare between the 3D scenes, whether the proper perspective is found or not, or how bad the perspectives differ from each other, or how good the perspectives are similar to each other. And I think they are close enough. And I will also like your manual review after what you are seeing in this presentation. So let me know what you think. Any type of comments or questions are welcome. Thank you for attending.